Hi everyone, Big Mac here. Welcome back to my favorite pre-calculus test questions. It's been a while since I actually posted the questions, so if you need a refresher, please go back, check the previous video in this playlist, or just the video that has all the different questions beforehand. So what I'm going to be doing in this video is I'm going to be going over the first questions, the questions that I covered in exam number 1 that I had on my introductory video. So of course, what is this again? These are questions that I used in a college pre-calculus class, so that covered the basic minimums of the algebra and the trigonometry that you needed for a proper course in calculus. So again, I assume that students had algebra skills through Algebra 2 in high school, through up to the geometry level. I needed them to have at least some base knowledge, and admittedly the first test made sure that it had that base knowledge covered, plus some of the introductory things that we have been talking about. So on our first question, I asked students, solve an algebraic inequality. Find the values of h that satisfy this inequality. We had 1 over h plus 1 minus 1, or h over h minus 1, and then that difference has to be less than or equal to -1. Find all values of h that satisfy the inequality. So admittedly, students in general freak out when they see inequalities. They remember these weird rules that don't always make sense. But let's just go over the basic things. What's going on with an inequality? How is it different than a regular equation? How is it the same? What are the important things that we need to take away from it? So in general, how to solve an inequality. If we have two numbers, a and b, and if a is less than b, what are the things that we can do? We can add or subtract something to both sides, just like a regular equation. That does not change the inequality. That does not change the sign of the inequality. Likewise, we can multiply both sides by a positive number, and that does not change the sign. So, often in school students learn like, oh, if you multiply or divide by a negative, then that reverses the sign. Basically, you're just subtracting both things to the other sides, and so you're just moving all your variables around and keeping the sign the same, which, some people just interpret as just flipping the sign around. So, of course, how do we normally solve these inequalities? We have to follow some regular rules that are, again, very similar to what's going on when we solve a regular equation. Set one of the sides equal to 0. Again, the proper way to do this is to subtract everything onto one side. Likewise, we need to find critical values. This can either be through factoring or just looking at the different things that are in the numerator and denominator to figure out, in what cases is the numerator going to change from positive to negative? In what places is the denominator going to change from positive to negative? How is that going to affect our function overall? So we need to find those critical places where the numerator might be 0, where the denominator might be 0. And based on that, we can use these test values. We can make a chart. We place them in order, pick regions or pick points in between each region determined by our critical values, and from there we can say, okay, this part's going to be positive, this part's going to be negative. Sometimes it has that nice positive negative pattern. So depending on the question, it may or may not. And from there we can go ahead and solve our inequality practically. So, things not to do. So in general, don't multiply both sides by an algebraic factor. Again, there are exceptions, of course, to everything if you know it's going to be a positive thing. But if you multiply both sides by x, you don't know if x is positive or negative. Then you would have to break it up into two separate cases. One where x is positive and your sign stays the same, or the other case where your x is negative and then you have to flip the signs. Don't worry about that. Subtract things. Get everything onto the same side first. And then you can start working towards it. Likewise, squares and square roots, they do not work like in a regular equation. You can't just take a square root on both sides and hope that the thing in the middle doesn't change, because it probably will. But that being said, for our particular problem, we needed to get everything onto the same side, and admittedly we have our algebraic expressions. We need to find a common denominator in order to add and subtract these fractions properly. That hasn't changed. So we can first just add +1 to both sides. So now we have everything over here on the left. We need to get everything to a common denominator, at which point we can add and subtract our fractions. So we have a factor of h plus 1, and over here we have a factor of h minus 1. So then for our common denominator on all of our terms, we're going to have it be h plus 1 times h minus 1, which is the same as h squared minus 1. So multiplying our left fraction by h minus 1 over h minus 1, we get this resulting fraction. Likewise, for our second fraction, we have to multiply top and bottom by h plus 1 over h plus 1. And then for our plus 1 itself, 1 is just a fraction, 1 over 1, we have h times 1 times h plus 1, or h minus 1, h plus 1, in both numerator and denominator, as we see here. Again, this whole thing over here, h squared minus 1 over h squared minus 1, that's just 1. So now that we're combining all of our like terms, we have a common denominator. We can add our fractions together. Yay. So admittedly, just a little bit of algebra. Make sure you're careful with your negative sign. You're distributing your terms. Things actually simplify quite nicely. We get negative 2 over h squared minus 1 being less than or equal to 0. Or likewise, if you want to, get rid of that negative sign, we get 2 over h squared minus 1 being greater than or equal to 0. So that being said, we now have our algebraic expression on the left side. It's simplified as much as we can. So now we need to figure out what are the really important values of h that is going to affect our function. In this case, we have if h is plus or minus 1, then our denominator will be 0. Obviously, we will have domain issues because of that. But in addition, depending on which side of plus or minus 1 you're in, we have less than negative 1, we have between minus 1 and positive 1, we have greater than positive 1. Your overall function could be positive or negative in that region. So you need to test each of those individual regions to see, hey, where does this inequality actually still hold true? So again, we know that we can't divide by 0, so positive 1 and negative 1, even though we had a less than or equal to inequality at the beginning, we cannot have plus or minus 1 in our final answer. We just can't. But like we mentioned already, we just plug in our test values separated by our different regions. So it turns out our inequality is satisfied for something less than negative 1, so anything from negative infinity to negative 1. Likewise, anything from positive 1 all the way through infinity, I plugged in a value for h, I evaluated the entire expression through, I made sure that it satisfied the inequality. So because of that, we got our final answer as h being anything less than negative 1, union anything greater than 1. So again, we could write that in a couple different ways, set notation, or as a absolute value inequality. I was comfortable with either one of those. How did students do? Not well at all, because admittedly the first step that almost every student did was they just multiplied everything through by h squared minus 1. They're like, it's mostly positive all the time, everything will be fine. Not always, especially when you have an expression like h squared minus 1 where part of it's negative, depending on your value of h, it could either be negative or positive. That's going to mess up your inequality. You might lose a solution set, you might gain a wrong solution set, stuff like that. Likewise, adding and subtracting fractions, people had a hard time with those. This is Algebra 2, people. You should be comfortable on how to do those by now. That being said, though, sometimes I had students who only worked on the left side. They tried to simplify their terms, and then they had a product of two things in the numerator and the denominator, but they set their products equal to negative 1. So going back up here to our original equation, they only manipulated the left side here and got stuff to factor up to negative 1, which I'll mention and again in a future problem is not a good thing to do ever, but admittedly not that great. So students who actually took the time to follow the procedures, do their test intervals, students had calculators. They could graph these things and figure out, oh, my answer makes sense, oh, my answer only kind of makes sense, how did I miss half of the solution? Students have their calculators as a way to check everything through. Of course, I required them to show full work in order to get full credit. But, that being said, that was the inequality question. Could have gone better. Could have gone a lot better. So, question 2 is just a series of true-false questions. Again, I included more of them on the actual exam, but these are the ones that I thought were the most important. for students. So true or false, if we have the product of two things, x to the 7th minus 3y, 10x plus y to the 6th, if we have that the product of these two things is 12, is it true then that either that first term, x to the 7th minus 3y, has to be 12, or that second term, 10x plus y to the 6th, has to be 12? Is that true or false? Likewise, for all values of x, is it true that if we take 2 times 4 to the x, we get 8 to the x? And then lastly, our solution set for the inequality x squared being greater than 49, well, we can say that x is between negative and 7 and infinity, which means that x is greater than 7. Sorry, x is greater than negative 7. And also we have the set from 7 to infinity such that x is greater than 7. So let's talk about this and see how that relates back to what we saw back on the previous problem. But for these true-false questions, they were all false. And admittedly, there was a lot going on behind these problems that, again, a lot of students assumed things that they thought they remembered from Algebra 2, which it usually turned out they didn't. So let's look at the first one really quickly. So let's look at what is the zero product rule. Why do we always try and get our equations and our inequalities, why do we always try and get a zero on one side? We try and get things with 0 on one side because 0 is a nice number with nice properties. Namely, if you multiply anything by 0, that's still 0. And assuming it's a finite number, you know, we're not talking limits or anything like that. But if you have a product of two things, a times b, and you know that that product is 0, then it has to be true that either the first product is 0, sorry, the first term of the product is 0, or the second term of the product is 0. There's no way around it. So admittedly, a lot of students think that, oh, if I have a times b, product of two things is 12, then either the first thing is 12 or the second thing is 12. No, there's really no guarantee of that whatsoever. So admittedly, if we had a times b is 1, or 12 in our case for the problem, it's possible that one of them is 12. But it could be any other, possibility of things that multiply together to 12. If you think that the only thing that multiplies to 12 is 12 in itself, you need to go back and learn about your prime and composite numbers and stuff like that. You could have had 12 times 1/12, negative 2 times negative 6. There's not enough information to tell us that, oh, one of these factors has to be 12. Right off the bat, there's just no guarantee on that whatsoever. So that being said, that first statement, definitely, absolutely false. Plus, I made these as, tried to make these pretty convoluted looking just to, try and help students realize the product of the first thing and the second thing, regardless of, how simple or complicated it looks like. We have to follow the zero product rule essentially still. Likewise, for problem number 2, we saw that the answer was false. But how did students think about that? Well, this problem ultimately just goes back to our regular procedures of order of operations when we're working with algebraic numbers. So, different schools teach it in different ways. The one they always taught me was the PEMDAS, P-E-M-D-A-S method, which was just an acronym for parentheses, exponents, multiplication, division, addition, subtraction. So when you're performing just regular arithmetic, there was a certain rule or a certain order of which you had to do things in order for things to work out. So obviously the first set is parentheses. If there's anything in parentheses, make sure you compute those first. Likewise, we have our exponents. We just take our terms, we take our base, take our exponent, we evaluate those things first. Hence, this is the reason why if we had the expression 5x squared, this is why it is 5 times x squared. X squared is its own thing. It is not 5x times 5x. Likewise, our next step is multiplication and or division, whichever happens to come first. The rule is we just go from left to right. The division does not have to come second. It can be just a mix of multiplication and division. The multiplication does not have to be done first. Just whatever is occurring first, left to right. Likewise, same thing with addition and subtraction. Just whichever one pops up first, you go ahead and compute it. You don't have to do the addition first. You shouldn't do the addition first. So, obviously, you've probably seen like Facebook questions and other stuff, other things like this where it's like, oh, 80% of people get this problem wrong. And then you will inevitably get this huge argument about like, oh, order of operations, I think I know PEMDAS, I really know PEMDAS, I'm a math teacher, et cetera, et cetera. So why do we try and, get to this particular notation? Because when we talk about functions, we need to follow a specific strategy. So, if, for example, we have some function f of x, if we have a shift by some value of h that's going to affect our graphs in the horizontal direction, we can multiply these things by some coefficient which will affect things in the vertical direction. That will either flip our graphs around, stretch them up, shrink them downward. We have a certain order of things, or we have to express our things in a certain order so that we don't confuse ourselves and we don't have any ambiguity. Because admittedly, ambiguity is one of the major problems why, you see thousands of people arguing on a Facebook question like that. Likewise, for polynomials, if we have 2x squared plus 9x minus 12, I'm not saying take 2, multiply it by x, then square that whole thing, then add 9, then multiply that whole thing by x, then, subtract 12. Because ultimately that would become like a nested loop that looks, quite different from what we have over here. So again, we have things like, things you might see on Facebook and people arguing about it. I'm not going to go into that discussion right now. I think the answer should be 8. But anyway, so thus, we're going back to our original question. If we had 2 times 4 to the x, exponents come first. So 4 to the x, even though it's an exponent, it's not a polynomial function, it's an exponential function. You have 4 to the x. That's just its own thing. It's just 4 to the x, and then you're multiplying it by 2. You do not do 2 times 4 first. I mean, if you plugged in any value of x besides 1, then you would hopefully see that this thing is absolutely false. Likewise, going back to our third inequality, dealing with square roots and inequalities. So if x squared is greater than 49, then x is greater than plus or minus 7. I wish it were that easy. I really wish it were. But again, students see this and they try and think about it in terms of just a regular equation. You take a square root on both sides, you add the plus or minus on the other side, you're done. I wish it were that simple. But in order to deal with this, we have to follow the same kind of procedure. Get everything on the same side. Find a way to simplify your expression. Maybe factor it out. Stuff like that. Find your critical values. So, likewise, x, if we subtracted both sides by 49, we get x squared minus 49 has to be positive. That factors as a difference of squares, x plus 7, x minus 7. So that tells you that, yeah, we knew that positive 7 and negative 7 were going to be our critical points for this thing, but we have to check every region in between them. So everything to the left of negative 7, everything between negative 7 and positive 7, everything greater than positive 7. So the true solution is everything less than negative 7 and everything greater than 7. Trying to just go to a shortcut here, you get like a mostly right section with some wrong parts and then a redundant also right section. It just doesn't help at all. So admittedly, how do students do on these kind of true-false questions? For the most part, I think they did pretty well. Though again, inequalities will always continue to confound people. But that being said, I thought that these 3 true-false questions kind of harken back to just basic algebra things. So things before, things that people should definitely be comfortable with before they try and step into a pre-calculus environment. And I just noticed that, like, of the students who missed 2 or 3 of these true-false questions, they did not do well because they could not do basic algebra 1. So, it was hard to, most of them saw, part way through the semester after the first midterm that this was not going to go well and that they had to, take another level math class instead of the one that they were in. Unfortunately, sometimes students think they're a lot more prepared than they actually are. And that was why I wrote this test. For students to realize, no, you actually don't remember it as well as you think you did. But that is the end of this part 1 video. This is Big Mac saying, later.